Good evening, everyone. This is the first public talk of AstroCamp for 2022, and I'm Catarina Marques, as you already know, but I'm here to talk to you about the Fisher matrix analysis in engineering and astrophysics. But the first questions that should come to your mind are, what are the Fisher matrix and why we need them? But let's first talk a little bit about the data and the knowledge that we have nowadays, and then I can introduce you to the Fisher matrix, and you will certainly understand why we need them and how we use them to make forecasts for our telescopes. So if we go back almost 100 years to 1929, we have to discover that our universe is expanding by Hubble. He formulated the Hubble's law that shows us that the farther a galaxy is, the faster it receives. But if we move on to 1998, almost 20 years ago, we have to discover that our universe is expanding, but with increasing speed. So these two different themes at the same year, and through type 1a supernovas, which are astrophysical objects with intrinsic brightness. They use them to observe the brightness and measure the distance between them. So if we go back in our time machine and return to the present, we have observational advances. We can, based on the first observations of the expanding universe and the cosmic microwave background radiation. So we can define a new era of the cosmology, modern cosmology. In this new era, we have to reject some of the theoretical predictions, but in the other hand, we have the improvement of the others. And with all of these improvements, we can reach a standard parameterization of our universe called the lambda cold dark matter model, the lambda CDM. So this model is the simplest available model consistent with the observations made so far. And this model tells us that our universe is composed by photons, neutrinos, the common matter. We have the baryons and leptons, and the cold dark matter, which is the matter that is non-relativistic, which only interacts gravitationally, and we have the dark energy. But this leads us to one of the main paradigms of the cosmology. That is that our universe is monopolized by two unexplained elements, the dark matter and the dark energy. And both of them has been discovered statistically in cosmological and astrophysical observations. But in fact, they have not been yet discovered experimentally, that is in the lab. So we have the dark matter responsible for forming the structure of our universe. But we also have the cosmological constant in our model, the lambda CDM, which is correlated with the energy density of the vacuum, this density is also associated with the dark energy. So we have in here the presence of the dark energy and the dark matter in our model. But this cosmological constant, the lambda one, is the simplest explanation consistent with the available data that we have so far for the source and the acceleration of our universe and its origin. So right now we have our cosmology, and we have the main goal to obtain the model that describes our universe with the smallest possible uncertainties of the parameters. But how can we work with these uncertainties in our parameter models? We have to use the Fisher matrix. And right now I can introduce you to the Fisher matrix itself. It looks like this, but it's a generical formula, and we have to assume a set of parameters, the P1s, of model M with n observables, with f measured quantities. There is the predictions of the model for the n observables, and with the associated uncertainties, the sigma ones. But this is just a mathematical formalism, right? So what can we actually gain from it? So we use the Fisher matrix analysis to predict the cosmological impact of a given set of observations. There is that we can predict the uncertainties with which we will constrain our cosmological parameters with the future measurements. I have a quote in here said by Whitman that the whole point of the Fisher matrix formalism is to predict how well the experiment will be able to constrain the model parameters before doing the experiment, and in fact, without even stimulating the experiment in any detail. We can then forecast the results of different experiments and look at the trade-offs such as precision versus costs. In other words, we can engage in experimental design. So right now we have the Fisher matrix, as you remember, but we need to get the uncertainty itself. So we need to use another mathematical formalism, the covariance matrix. And as you can see in here, the mathematical formalism is just inversion of our Fisher matrix. But to simplify our life, I will assume a model with two parameters, the x and y, and you can see only two parameters in there. And the sigma x and the sigma I are the 1 sigma uncertainties that correspond to 68.3% of our confidence level in our parameters, the x and y that we have assumed. So this covariance matrix gives us an estimate of the covariance of our parameters. So in this, with this covariance matrix, we can also, oh, sorry, I forgot to tell you this. In fact, in here, we have a different correlation coefficient that shows us how correlated are our parameters. So if we have the correlation coefficient equals to -1, we have independent parameters. But if our parameters are completely correlated, which implies a correlation coefficient equals to +1. So now I will show you that we can draw, in fact, the confidence ellipses as well. We only have to describe our radius of the major and minor axis and the angle from the positive x-axis to the ellipsis major axis. This is a way to see visually how our confidence area in the parameters by a draw. So we already have the Fisher matrix, the covariance matrix, and the confidence ellipses. But in our Fisher matrix analysis, we need to go further and get the figure of merit. The figure of merit actually is extremely important due to its inverse proportionality with the confidence area of the two parameters of our model that we assume, the x and y. So if we have a huge figure of merit, it will imply that we have a small confidence area. And we also imply that we have small uncertainties in our parameters. So it's the goal, right? Small uncertainties in our parameters. So I have introduced you the Fisher matrix analysis. And now I want to introduce to you a particular case in astrophysics. In fact, it's my master thesis that I've done in this here, entitled as Optimization of Spectroscopic Tests of Fundamental Physics from Espresso to DLT. I use the Fisher matrix analysis on measurements of fundamental physics, astrophysical tests. In fact, I use the redshift rate and fine structure constant, the alpha one. You probably don't know them, so I will explain you a little bit about them. So we have the redshift that results from the expansion of the space itself and not from a movement of a body. That is that we can have two galaxies static in space and nevertheless they experience the redshift if the space itself is increasing. But this redshift follows our cosmological expansion, and by varying on time, we'll have a redshift. So this measurement will, with this measurement, we will have effectively determined our acceleration of our universe. And now I have the fine structure constant. This coupling constant measures the strength of the electromagnetic force that describes how electrically elementary particles and photons interact with each other. But this constant has a particularity that if it changes in space-time, it will imply a violation of Einstein equivalence principle. And as well, this will imply a questioning of all four forces of the nature and a rupture of the gravity as we know it. So we have this, and as you can see in title, I used two different high-resolution spectrographs. The espresso one, which is in VLT, the Very Large Telescope, which also recently went into operation. So you can use the data from him and the knowledge from him to use to the future high-resolution spectrographs, the hundreds. The 100 seat will be installed in the extremely large telescope, the successor of the VLT, and the technical first flight of the VLT, it will be planned about in 2027. So with these two, we can have these scenarios. For redshift drift, the current installations of Espresso only allow sensitivity some orders worse than the expected signal, so we cannot have the redshift drift. But with Andes, we will have the direct measurements of the expansion of our universe. But for variation of alpha to define structure constant, we have two possible scenarios. We have Espresso that cannot detect the variation of alpha, and Andes will get paracosmological constraints, which implies constraints on energy and dark matter, or we can have these parts, the detection by Espresso and Andes, although do the paracosmological constraints, will also mapping the variation over the entire possible redshift range in different environments. So right now I can present to you the two datasets that I use for the redshift drift measurements, the Joule-Lisk approach and the golden sample. The Joule-Lisk approach is just an approach for the uncertainty of the velocity. I don't remember the first name. Spectroscopic velocity, sorry. So we assume 5 different effective redshifts in a time span of 20 years. But for the golden sample, it's quite different. We have our uncertainty in the spectroscopic velocity only always equal to 22.8 centimeters per second, because we have a catalog of 30 bright quasars with a time span of 25 years, and it's still under research, so it's not done yet. So with this, I can introduce to you to my first results, the forecasts of the redshift drift measurements for our lambda CDM model, where we have the H parameter and the omega m parameter. The H are the reduced Hubble parameter, and the omega m is the present time matter density. And as you can see in here, the golden sample is the least competitive for this parameter, the omega m, because it has a larger ellipsis, and you can see as well in here, we have the lowest figure of merit obtained. So it's been implying this largest area, as I told you before, if you remember. Now I can introduce to you another model. There is the CPL. So we have the H and omega m as well, where we have W0 and WA. This corresponds to the dark energy equation of state. The W0 is the present value, and the WA is the coefficient of the time-dependent term. And you can see in a few results and in the table that we had some cosmological parameters, if we had more, we will have smaller constraints in pretty much the same, and the figure of merit will also decrease as well, because it will have smaller constraints, the signal-wise. So now I can introduce you the stability of alpha, so the variation of alpha. I use the Bekenstein model, where we have the omega m, the zeta m, and the zeta lambda. And in fact, the zeta m and zeta lambda are the parameter combinations constrained by alpha measurements. You can see in here, the light blue is the optimistic forecast for them, and the dark blue is the baseline ones. And as you can see, both of them are equality sensitive to omega m parameter, but as you can see in the left panel, the optimistic forecasts are more sensitive to both zeta m and zeta lambda compared to the baseline ones. Oh, and you can see in here, we don't have nothing to declare about the omega m parameter. And right now for CPL, we have the zeta parameter, which corresponds to the scalar field coupling to the electromagnetic sector. And we have the same colors as the previous slides. So the sensitivity to omega m, the W0 and WA is the same for the two forecasts, the optimistic and the baseline ones. But as we predict, the optimistic forecasts lead us to a better zeta constraints than the baseline ones. So I also combined the measurements, the redshift drift and the alpha measurements. And as you can see in here, I have in red the redshift drift measurements. I have in light purple the alpha measurements for baseline, and in dark purple the combination of the redshift drift, the least one, and the alpha baseline. But as you can see in the panel selected in red as well, the upper right panel, you cannot distinguish three of ellipses, right? So they are all overlapped, which implies that the gain of the combination is very small. We cannot distinguish them. So the biggest gain is actually in the omega per meter, as you can see here. If we have the combination with dark purple, we will have better constraints on omega per meter. So I can tell you that my results were relevant to and this phase B of construction, and my code for the Fisher matrix analysis will allow us to study in detail the scientific potential of the spectrograph. But in fact, I want to show you one more thing, that the Fisher matrix is also applied in many areas, and as well as engineering, we can apply. I want to show you 3 examples in neuroscience, optics, in machine learning, plus acoustics. But you can have that the Fisher matrix has application in many areas. So in neuroscience, actually, the main goal is to understand the representations formed by brain activity patterns and their connection to the behavior. So the classical approach they have is to investigate how individual neurons encode stimuli and how their tuning determines the fidelity of the neural representation. So the tuning analysis often uses the Fisher matrix to characterize the sensitivity of the neural responses to small changes in the stimulus. Now I can introduce you to the optics one. The main goal is to achieve optical super resolution, but in what? In optical instruments such as telescopes for us and microscopes. So the Fisher matrix are quite interesting in this case because it refers to the quantum measurements and allows the optimization of all thinkable measurement schemes that we can have. And the last one, the machine learning plus acoustics, we have the main goal to characterize the ocean environment by estimating environmental parameters. Actually, this is a master thesis as well. And he's studying the acoustic signals of the ship noise spectrogram data. He used them to predict how are the ocean's environmental parameters and all this stuff, and to try to estimate it, how smaller can be the uncertainties in this. So the Fisher matrix allows us to achieve a lower bound on the uncertainty associated with the environmental parameters estimated. So we know now how to do a Fisher matrix analysis, right? You also have my application in astrophysics, and you know that we can be done in many areas, and I show you 3 examples in engineering. So this ends my presentation. Thank you so much for your attention. Questions? So many questions, stop. E foi mais rápido.
Anybody have questions?
Did you enjoy working on this project?
Yeah, sure. I will do a PhD in that as well.
Do you want to work with this in the future? And with the future with it?
You or me?
You.
Oh, me, sure, in a PhD in astronomy or physics PhD. I will do some more analysis with this. Yeah, sure.
No more questions?